Welcome to Session 3 on noise coupling equivalent circuits. In Session 2, we talked about how there are 4 basic coupling mechanisms: conductive, electromagnetic wave, magnetic field, and electric fields. In this session, we're going to try to identify the equivalent circuits that describe each of those 4 basic problems. Once we've identified the noise coupling equivalent circuits, then we will know which parameters affect those problems, which parameters we need to consider adjusting. As I've just reviewed for you, there are 4 basic coupling mechanisms: conductively coupled noise, which involves two or more metal contacts; electromagnetic wave coupling, which involves a distance greater than a wavelength. We need to be in the far field. Magnetic field coupling, which we also call inductive or mutual inductive coupling. Magnetic fields are generated by currents. Electric field coupling, also called mutual capacitive coupling. Electric fields, we determined, were generated by voltage differences. The equivalent circuit for conductive coupling involves a noise source which is connected by 2 conductors to a susceptible circuit. We represent the susceptible circuit here by some equivalent impedance. Normally it's a very complicated circuit which we have simply boiled down into this one equivalent impedance. And with conductive coupling, we have one path that carries the unwanted noise current over. And of course, as we said, all currents return back to their sources, so this same unintentional noise current has to return back on another path back to its source. The primary conductive paths are power connections, particularly DC power. That's the dominant, most likely conductive path. We need to do a very good job of filtering the DC power bus. Signal connections are also another possibility for conductive noise, or grounding connections. We're going to discuss grounding in detail in sessions 3 and 4, but I think you'll find that for signal grounding, we often tend to have too much grounding, too many grounding connections. And those additional grounding connections result in the possibility of noise currents having access to our signal path. Now, in terms of safety grounding, we're going to see that, well, there are pretty firm rules about what safety grounding requires, and we can't be changing that. But we do have a lot of control over the signal grounding, and by controlling signal grounding, we can therefore minimize or reduce a lot of our unintentional conductively coupled noise problems. In addition to talking about the equivalent circuits for each of these problems, we're also going to talk about some of the standard symptoms or clues that show up to help us identify which problem is occurring. In this situation, let's assume we have the noise voltage displayed on our scope. We have voltage, noise voltage versus time. The signal on this circuit has somehow been turned off, so we're now just concentrating on the noise. The noise is going primarily one polarity. What that indicates to us is that the noise voltage has a DC average value, a non-zero average value. Well, how is it that zero frequency can be coupled from one place to another? You can't couple zero frequency magnetically or electrically or through electromagnetic waves. So if the noise spectrum, not the signal spectrum now, but the noise spectrum, if it contains zero frequency, then there's a very high probability that that particular process, that particular coupling, is conductive. And that's what this is indicating. The average value being present, being non-zero, is a strong suggestion that we're dealing with a conductively coupled problem. Now you could say, wait a minute, it's more than a strong suggestion, it's a certainty that it's conductive. No, life's not that simple. You see, what if we had some type of radiative coupling? Radiative just means noise through the air. Noise through the air, we've already said, could be of 3 types. It could be electromagnetic waves, electric fields, or magnetic fields. What if we had radiative coupling getting into a circuit? How could radiative coupling, which of course can't have a DC level, how could that generate a DC level? Well, if the circuit was able to rectify the noise, then once it's been rectified, we will generate a DC level, and of course we'll also have all the modulation components showing up in the circuit as well. So in the previous example, we did not know necessarily that it was not something coupled in, say, magnetically and then rectified to generate the DC level. We don't know that. But also, most noise problems happen in the simplest manner possible. To have something couple in and then become rectified is quite a bit more involved than simply being directly conducted. So I would say the highest probability is if there's a DC level, a DC offset produced by the noise, that's a 80% or better probability it's a conducted problem. Now, you can sometimes tell from the level. If the DC that's being produced by the noise, if that's 10 volts, why, it's not likely that that's a rectified RF or AC frequency of some kind. It's a very strong level if it is. So 10 volts DC would pretty clearly indicate it's a conducted problem that's being rectified. 2 or 3 millivolts of DC level, yeah, we can get that by rectifying a low-level RF signal possibly, or rectifying a low-level magnetically field-coupled problem. So the level of the DC might be an indication as to whether it's possibly conducted or not. Another one of our problems is electric field coupling, which I'm now here calling it capacitive coupling because we're going to talk about it from its circuit's point of view. So remember, electric field coupling would be the same as what we're talking about here. So we want to know what equivalent circuit is necessary to produce electric field coupling. So if you just were to think about it for a few moments, it might almost be obvious. We need a source of electric field. Well, a time-varying voltage is what generates an electric field. We need one of those. Then we need a way to couple the electric field from one circuit to the other. The electric flux coupling, in this case, is represented as a mutual capacitance between the two circuits. That's electric flux coupling. That's just a circuit's description for that. That's a mutual capacitance. Now, if we take this mutual capacitance, multiply by dV dt, then we have C dV dt is a current. This is a current which the noise generator injects into the susceptible circuit. This impedance right here represents the susceptible circuit. Now you could say, wait a minute, doesn't the impedance of that circuit have something to say about how much current's going to flow? Well, theoretically, yes. Practically speaking, no. Normally, the coupling we are talking about here is not a desirable, intentional, high level of coupling. This is hopefully a very small, well, we'd like it to be zero level of coupling. But this is a very low coupling we're intending to achieve here. So with the light coupling, this impedance right here dominates in most instances over this impedance and is the factor that limits the current. Now I realize this is not always true, but it's generally true. So what we're going to say is that we have electric field coupling looks like a constant current source. Not constant in time, but constant in RMS amplitude. And that's kind of a surprise in a way. The electric field is generated by a voltage difference, but what the electric flux injects or induces into the neighboring circuit, it doesn't induce directly a voltage. What it does is it induces or injects a current, and then as that current flows through the impedance of the circuit, then it produces the voltage. So another thing we need, of course, to have a problem here is we need some equivalent impedance across which this current can develop a voltage. And finally, we need a return path for the current back to its source. So electric field coupling needs 4 basic items. You need a time-varying voltage to generate the electric field. You need a mutual capacitance to couple the electric flux unintentionally from one circuit to the other. You need a circuit impedance across which the induced current generates a noise voltage. And then you need a return path for the noise current back to the source. And that's what we were seeing here. 4 basic elements. Now let's try to figure out how to describe or think about the equivalent circuit impedance. The equivalent circuit impedance of the susceptible circuit. Here we have an AC power line, which unfortunately maybe is a little bit close to a signal line. Because of the close proximity, there's a mutual capacitance between the two conductors. It's, again, not intentional. Probably doesn't appear on any schematic diagrams, but still a mutual capacitance. The AC line voltage can drive a current through this capacitance into the susceptible circuit. Now the susceptible circuit is represented as having a source impedance on one end and a load impedance on the other end. Now notice I don't show any wiring impedance here. In the first session we spent a lot of time discussing the self-inductance and the self-capacitance of the wiring and so forth. And here I just kind of completely ignore all that. Well, in a typical situation, the impedances on the end of the circuit should control the current in the circuit. The impedance of the wiring should not control the amount of current, but it does control where the current flows. It's the path of the current we were interested in earlier. But even so, and we're still interested in the path of the current here. In this case, it's the path of the capacitively coupled noise current. But in most situations, I think you're fairly safe to neglect, at least as a first approximation, neglect the impedance of the wiring itself. Just concentrate on the impedance of the source and load end. At lower frequencies, say kilohertz frequencies, and for shorter cable runs, like cables of 50 feet or less, that's definitely true. Now you get up into the megahertz range or you get up to hundreds of feet of wiring, then we probably can't totally neglect the impedance properties of the wiring. But I would say as a very good first approximation, we can just ignore the properties of the wiring, concentrate on the source impedance and the load impedance. Now notice what happens to the capacitively coupled current. The capacitively coupled current, once it gets into the signal circuit, divides. Some of that current goes through the source, some of that current goes through the load. And then these two currents come back together and somehow return back to their source. The return path a lot of times is a shared signal common signal return, or possibly even a grounding connection. But here's the important thing in this diagram. Notice how the current divides, partly to the source, partly to the load. That means those two impedances are connected in parallel as far as the capacitive noise current is concerned. From the signal current point of view, the source and load impedance are in series. But we're not looking at this problem from the signal current perspective. We're looking at it from the perspective of the capacitively coupled noise current. From that perspective, the two impedances are in parallel. That tells us the equivalent impedance we're looking for here is the source in parallel with the load. That's how we evaluate the impedance of the susceptible circuit. Put the two in parallel. And we do it that way because that's simply the way the electric field coupled current sees the problem. All right, let's talk about how to diagnose capacitively coupled problems. What do we look for to identify that this is our difficulty? Well, the number one thing to look for is the equivalent impedance of the susceptible circuit. We usually know that. That's information that we have available to us. And that's our number one indicator as to whether we're going to have an electric field coupling problem. The larger this impedance is, then the larger the voltage that will be developed when this fixed amount of current goes through that impedance. So if the equivalent impedance is maybe 1 ohm, and our signal level is no more than, say, minimum resolution level no more than 10 millivolts, probably we don't have much of a problem. On the other hand, if this equivalent impedance is 1 mega ohm, and our minimum signal level is 10 millivolts, there's a very good chance we're going to develop more than 10 millivolts across here, and this will be a problem. So just by knowing the equivalent impedance of our circuit and the signal level we're dealing with, the minimum signal level, we can have a pretty good idea of whether electric field coupling will be a problem or not. Now, once you've identified that you have what appears to be an adequately high impedance susceptible circuit, what do you look for next? You look for a source of electric field, which is a voltage. Are there voltages in the area that can generate electric fields? Usually there are. How fast are these voltages switching? The faster they're switching, that is, the higher the frequency, a little bit bigger problem. Are there exposed metal surfaces on either the noise generating side or the susceptible side? Exposed metal surfaces adds to more capacitance between the two circuits. Floating metal, we'll discuss this in more detail later. Floating metal increases capacitive coupling. We'll show how that happens later. Does the noise current have a return path? In this case, there is one indicated here. Maybe this is a grounding connection. A return path. There needs to be some kind of path to return the noise current back to the source. people moving around, do they affect the noise level? Later on, we'll show you that this is clearly a symptom of a capacitive coupling problem. Usually, to identify a capacitive problem, you really only have to find two things. Find a circuit with a susceptible equivalent impedance that you judge to be moderately high. Find at least one voltage source in the area where there's switching going on or some frequency involved, and that will likely indicate the possibility of this kind of problem. Now, I think diagnosing the problem is the hard part. I imagine, though, most of you are more interested in reducing the problem. Well, there are obvious ways to reduce this problem. If we know what's causing the problem, we know then what we can do to control it. In this situation, the first thing to look at, I suppose, is the leading item that indicated we had a problem was a high equivalent impedance. Why don't we now take a look at that as a leading way to control the problem? Let's reduce that equivalent impedance. Now, what we've got to remember is this impedance was selected in order for the circuit to operate in a particular manner. This is our signal impedance. Maybe we don't want to reduce the impedance. Maybe that's going to have an adverse effect on the signal. So possibly we want to reduce this impedance at the noise frequency but not the signal frequency. Of course, if we had high frequency noise, low frequency signal, we could put a capacitor across here and thereby reduce the impedance at high frequency but not reduce it as much at low frequency using a filtering technique, which is a standard approach. We could also try to reduce the noise voltage if that's adjustable. Reduce the impedance, reduce the voltage, reduce the frequency of the noise, again if that's adjustable. Reduce the mutual capacitance, spread the circuits farther apart. We could try to disconnect the current return path, break the noise current return path. Now this is one that doesn't work as well as you would think. You would think if you disconnected this path right here that the noise current would stop completely and the noise would go away. But no, when you break two wires apart, you don't have a purely open circuit, do you? You have some capacitance between those wires. And you can say, well, I can spread those wires quite a ways apart and reduce that capacitance. But actually, there are probably other capacitors shunting the path you're currently looking at that results in there being still considerable capacitance. So when you find the current return path, the noise current return path, when you disconnect that path, I think you're going to be disappointed at how little reduction there is in the coupling. For example, going back to the circuit, let's say this capacitance here was 20 picofarads. Let's say when we break this circuit apart, we get a capacitance here that's 500 picofarads. Well, 500 picofarads in series with 20 is still a short circuit, isn't it? We're thinking that we're dramatically lowering the impedance, or raising the impedance actually. We're dramatically raising the impedance by disconnecting that wiring, and actually we're not doing that. We're making very little change. So we get about the same amount of current continuing to circulate, and we get about the same amount of voltage across the equivalent circuit, even by opening up that path. Now, we could consider this. I mean, if you can see that you can break open this path and replace the short circuit here with a very high impedance compared to the other side, a very high impedance, then breaking this noise current return path would be a good option. But be prepared for a lot of disappointment there. Sometimes we're not able to open that circuit up as much as we would think. Another way to fix the problem, which is not obvious from this diagram, and that's why we have to talk about it in quite a bit of detail later, that's using electric field, that is capacitive shielding. Capacitive shielding is the only technique I've listed which you cannot see immediately how it's going to work. So the other 5 techniques, pretty clear how they fix the problem. So later on, we'll use some of these techniques. We'll discuss them a bit more briefly. But later, we're going to concentrate a lot on electric field shielding because that's the one that's not so obvious. What about magnetic field problems? How do they occur? What equivalent circuit would we expect to find? Well, again, we need something that will generate a magnetic field, a time-varying magnetic field. So a time-varying current will generate a magnetic field. But in order to have that current to be able to flow, there must be a path through which it can flow or propagate. So that current has to have a loop associated with it. Now that may be a very desirable loop. That may be either another one of our signal currents or somebody else's signal current. So a current flowing in a loop will generate magnetic flux. Let's assume that our circuit of concern, the susceptible circuit's over here. It also has a little bit of exposed loop area. So some of this magnetic flux, hopefully not all of it, hopefully a very small amount of it, but some of this magnetic flux magnetically couples into this loop, induces a voltage. The voltage induced can be related to the amount of current, the frequency of the current, and the amount of mutual inductance. But what happens is we get a voltage induced in the loop. We don't get current induced in the loop. A lot of times when I ask people how magnetic problems occur, does a time-changing magnetic field induce a current or a voltage in a loop? They often say the magnetic field induces a current. But that's not the correct physics. The correct physics is we get an induced voltage. Now the question is, what happens to this voltage? How does it show up as a noise problem within the loop? Well, the voltage drives the current around the loop, and the current produces a voltage drop across the elements that make up the loop. Wherever there's the largest impedance in the loop, that's where you get the largest voltage. Now in this case, we're looking at the load end. The load end of the circuit is where we're typically measuring the signal. If the noise produces the greatest contribution at the load end, that's where it's going to be more detrimental to us. So it's the impedance at the load end of the circuit that is critical here. The higher the load impedance is, the greater voltage is developed across that impedance. The impedance on the source end is of lesser concern to us. See, in the electric field coupled case, we were worried about the parallel combination of both impedances. It was the parallel of the two that controlled the situation. Here, the two are in series, but it's the load end is where we're mainly concerned about the noise occurring. That's where we're concentrating our efforts. So the larger the load impedance, the more detrimental the problem. Now actually the way it's written here is we take the voltage induced and we do a resistive or impedance divider approach, divide the voltage across the source and the load. So what indicates a problem then magnetically is significant amount of fast switching pulsing currents, a little bit of extra loop area, and a high impedance circuit, a high impedance load end on the circuit. Now in terms of what's the worst noise level, what's the highest value for the IDT, which is the worst, I have two examples here, switching 10 amps in 10 microseconds or 10 milliamps in 10 nanoseconds. Well, it's kind of a trick question in a sense because the IDT values are both 10 to the 6th. Both of these are very significant problems. We'd have to worry a lot about these two. Now they're not identical problems. This one here has most of the energy in the kilohertz range. This one has a lot of the energy up in the megahertz range. So the frequency spectrum over which they are a problem are different. But I would say both of these currents need to be routed very carefully and their loop areas need to be tightly controlled. My experience is that on a circuit board, for example, if we had these two currents present, we would spend a lot of attention and time worrying about the 10 amps and not enough attention probably worrying about the 10 milliamps. We would consider that insignificant in comparison. But all I can say is that these are both very troublesome, very serious problems. We'd have to be extremely careful how we route these two currents. What about controlling magnetic troubles? What can we do to decrease this kind of an effect? Well, the magnetic problem is caused by current, so we could reduce the amplitude of the current. But usually that's somebody else's current or signal and they don't want us messing with it, so we can't control that. We could try reducing the frequency of the current. But again, if it's somebody else's circuit, maybe we can't do that. We could try adjusting our load impedance, making it a lower value. But we went to a lot of trouble to get at what it is already, so probably we don't want to do too much adjusting there. Now we could put a shunt capacitor across the load, like we talked about in the capacitive coupling case, and maybe get some help that way. Use a frequency-dependent impedance adjustment. But really the best way to think about fixing magnetic problems is to do something about the unneeded, unintentional mutual inductance between the two circuits. All right, so let's take a look at how do we do that? How do we control mutual inductance? Well, starting at the bottom of our list here, we could add magnetic shielding. We could put a magnetic shielding material between the two loops and somehow control the magnetic flux coupling between the loops. If we're trying to control the problem at low frequency in the kilohertz range, it's going to take a high mu, very expensive magnetic material, high permeability material. If we're going to try to control the problem at high frequencies, megahertz, it just takes basically a good conductor. That's a lot cheaper, and that can work fairly effective. We'll show all of this in a later session about how to employ magnetic shielding. But if the problem were in the kilohertz range, then it's going to be a very tough solution because we're going to have to use an expensive material that might only give us a few dB of noise reduction. So I wouldn't put my first attempt at solving the problem on the magnetic shielding. I would save that to last, basically to a desperation effort probably. What else could we do? We could increase the separation between the loops. You pull the loops farther apart, the magnetic flux coupling between them goes down. But here we have the situation, can we really afford to make the system 10 times bigger than it currently is? Probably we won't keep our job very long if that's our only solution we can come up with. We're probably going to want to put more and more circuits, more traces, more signals on a board. We're going to want to cram things closer and closer together. Yet, what do we do about bringing down mutual inductance if the loops have to be put closer together? What if we can't increase the separation? Again, this is a good idea. Yes, if you can get another 10 feet between the loops, that'll make a dramatic difference if you started out with them 6 inches apart. But what if we can't increase the separation? What if we can't afford the costly magnetic shielding? Well, there is one very good solution left. Let's just reduce the size of the emitting loop if we have control over that, or reduce the size of the susceptible loop if we have control over that. You see, we have control over one of these two loops. If we don't, we're not interested in the problem. It's somebody else's problem. So if this is our problem, then one of these two loops is involved. Either we have the loop that is emitting the magnetic field, or we have the loop that is receiving the magnetic field. And if that's the situation, then what we want to do, we want to control the size of all the loops that we have control over. Just minimize those loop areas. I know it sounds almost too simple, but that's the way to control magnetic problems. Turning off the current's another nice idea, but we probably can't get away with that either. But controlling the mutual inductance by reducing loop area is the cost-effective way to control magnetic fields. Now let's say we have a situation where we know the problem is either magnetic field coupling or electric field coupling. Now let's see how we got to that point. Here is the circuit of concern. The signal source, and I don't show the signal source voltage because we're interested just in the noise here, but the signal has a source, a cable, and a load. What we've noticed is there are no external wires attached to this circuit. Or maybe if there were, let's say we noticed that you take the signal wiring itself, our signal wiring that we're concerned about, as we move this wiring through the air, the noise level fluctuates. So either because there are no external wires attached, or because moving the wires causes the noise level to fluctuate, that tells us that this is not a conduction problem. So we've eliminated that from our 4 options. Let's say the frequency of the noise is 10 kilohertz. Then it can't be electromagnetic waves. So we've eliminated that from our possibilities. So we've got 2 left. All noise troubles have to fit into these 4 patterns, So we've only got the possibility of magnetic field coupling occurring or electric field coupling occurring. Let's see if we can figure out which one of those 2 is involved. So what I've done here is I've taken the susceptible circuit and I've superimposed onto it the representation of the other 2 problems. We could have a switching voltage coupling in electric fields through a mutual capacitance. We could also have a pulsating current coupling in magnetic fields through a mutual inductance. So we've allowed for 2 possibilities to exist, the remaining 2. Now I'm not saying that both of those are happening. One of those 2 is probably dominating. We want to know how can we diagnose, how can we determine which one of those 2 would be dominating. Well, notice, if the coupling is electric flux coupling, then the voltage at the source end and the voltage at the load end, those 2 voltages would be roughly equal and roughly in phase. On the other hand, If the coupling is magnetically coupled, then the voltage induced drives the current around the loop, and as the current goes around the loop, you get a different voltage at the load end and a different phase, a different voltage and a different phase at the load than you do at the source. So if the voltage at the two ends of the circuit are nearly equal and in phase, it's more likely capacitive coupling. If the voltage at the two ends, this is noise voltage, at the two ends of the circuit are substantially different, and that's associated with the impedances being different at the two ends, then that's a pretty good indication that it's an inductive coupling problem. Now, you wouldn't expect the voltages at the two ends to be 180 degrees out of phase if it's inductive. That would only be true if we had purely resistive loads. If there's reactance in the loads and, of course, a little reactance in the cable, then the phase difference between the noise at the source and the noise at the load wouldn't be exactly 180 degrees, but it would be probably more than a few degrees difference. So, by noting the noise level at the source and the load, the amplitude and possibly the phase, if that were measurable, you could get a good indication of the type of noise. Now, I know phase is difficult to measure, so I won't concentrate on using that as a diagnostic technique too often. But still, if this was a short cable, 4 or 5 feet long, if we had a 2-channel scope, we could put one channel on each end of the circuit and look at the amplitude and phase simultaneously. That would be a really good indication of what kind of noise coupling we're dealing with there. Let's try this problem where we have a ribbon cable, and we have a lot of signals on this ribbon cable, but we're currently only looking at 2. Only 2 of these signals are causing a problem. Signal 1 is the troublemaker. The current out on signal 1 returning on the shared path in the middle. That path is shared by signal 1 and signal 2. Let's say when signal 1 operates, there is noise obviously present at the output of circuit 2. So we know signal 1 is the cause of the problem. How could we identify what's going on here? How could we describe it? Well, this path right here in the middle, the shared return path, has resistance. I1 times R is a conduction possibility. Conductively coupled problem. That can certainly exist. Now, there can be magnetic coupling as well, but notice how I'm going to describe it compared to, I think, the way most people describe it. Most people would say that magnetically what's happening is the wire in the middle has self-inductance. They would want to talk about L di1 dt. But I don't believe that's correct. In fact, I'm sure that's not correct. The wire in the middle, that straight piece of wire, doesn't form a loop. Show me the loop. If you want to talk about self-inductance, I want to see the loop. All we're talking about here is we're supposedly talking about the self-inductance of a straight piece of wire. There's no loop there. There's no self-inductance to talk about. What I do see is I see current I1 flowing in a loop, and I see current or signal I2 flowing in a loop. I see 2 loops with a mutual inductance between them. So I think the problem is M di1 dt, not L di1 dt. Both of those techniques look very similar. It's quite often that we think we have a self-inductance problem when we really have a mutual inductance problem. And a lot of people think, well, it doesn't matter that much, so it's an inductance problem of one type or another. Who really cares about the details? Well, the solution is all in the details. We don't fix mutual inductance problems the same way we fix self-inductance problems, at least not completely. So we need to really understand carefully the physics of the phenomenon. The physics is critical. It's important to us. We have to keep that in mind. So this is a mutual inductance problem, and this is our magnetic coupling possibilities. Now, what about electric field coupling? Well, we have 3 wires here. If you took those wires 2 at a time, you could talk about 3 different capacitors. But I only show one on the diagram. It's about to get cluttered away here, but I show one capacitor from this wire to this wire. That's the critical capacitor. That's the one that determines how much electric flux coupling will go from circuit 1 to circuit 2. The other 2 capacitors, they are present. It would not be incorrect to put them on the diagram, but I'm going to leave them out. I don't want to needlessly clutter the diagram with parameters that are secondary and third order effects. I only want to put the primary parameters on here. So I'm going to allow for electric flux coupling. So C dV1 dt is a current that is induced into circuit 2. Now that current flows through the parallel impedance of the source and load in circuit 2. But I'm going to assume the load in circuit 2 is a very high impedance relative to the source, so the parallel combination is dominated just by the source. So here we have three different coupling mechanisms. The only one we don't have is electromagnetic wave coupling, and it's probably pretty realistic to leave that out. I'm assuming here that frequencies might be a few megahertz or less, and so there's no distances involved large enough to allow electromagnetic wave coupling. So the other three are possible. How could we determine, prior to building this circuit, which one of these three is going to dominate? Well, this could be pretty easily done. We can calculate the resistance of this wire if we know the wire size and length, so we can evaluate that number. We can calculate the mutual inductance between two loops if we look up the right formulas, and we can estimate this value. We can get the mutual capacitance between two parallel wires, so we can estimate all these parameters and decide in advance which of these three problems is going to be the worst of the three. Let's say for a moment we thought the problem was going to be capacitively coupled, and it actually was magnetic. Say we were kind of guessing at what the trouble was, and we guessed wrong. We have the three wires here now. Remember, they have to share a common path in the middle. So if it's electric field coupling that we're worried about, and if we could move those wires to reduce the electric field coupling, we would spread the wires apart. That decreases the capacitive coupling between the two outer wires. But you can realize now, if we were wrong, if it really was magnetic field coupling, then when we pull the wires apart, what we do is we open up the loop area. We increase the magnetic field, the mutual inductance between the circuits. One thing I'm trying to point out here is that a lot of times the solution for an electric field problem is not like the solution you would use for a magnetic field problem. In fact, sometimes they're quite different. So we have to know exactly which problem we're dealing with here. And in this case, if we think it's electric field coupling and we pull those wires apart, thinking we're going to reduce the problem, we're actually going to make it a lot worse. If it's magnetically coupled, then you want the wires pushed closer together. Now that's only because they share a common path. If you had two separate circuits consisting of two wires each, then to reduce electric or magnetic coupling, you'd take both wires and move them farther apart. You'd want each of the loops separate farther. But when they share a common path, then you'd push them all closer together. So again, we need to know exactly what the coupling mechanism is so that we can identify the correct solution approach. Now, let's say, for the moment, let's say R2, the source resistance, is very low. Not exactly 0, but almost 0 ohms. So I'm going to throw this one out for a moment. How could we tell the difference between a conducted problem and a magnetic coupled problem? Let's assume the circuit's already built. If the circuit's built, then I'm not going to spend a lot of time calculating things. I'm going to go out and make some measurements. So let's say that the current in circuit 1, let's say the current looks like this. I don't need to know exactly what it looks like. It doesn't matter exactly what it looks like as long as I have some idea what this is. If the problem is the resistance problem, if it's I1 times R, then that noise voltage is going to look like a pulse. It's going to look just like the current. On the other hand, if the problem is M dI1 dt, then we're going to see a positive spike and a negative spike on the edges. So if I know what this current looks like, if the noise in circuit 2 looks like the current, it's conduction. If the noise looks like the derivative of the current, then it's a magnetic field problem. So that would be a way that we could identify or separate these problems. Okay, we're talking a lot about source and load impedances here. The value of the source and load impedances has a lot to say, has a lot to do regarding the susceptibility to either capacitive coupling or inductive coupling. So let's talk a little more about what possible source and load impedances we could have and try to determine susceptibility for these different types of circuits. You could have a voltage-driven circuit. Voltage-driven. There we tend to have a low source impedance, not exactly 0 ohms, but a small value. And we tend to have a high impedance that we're driving into, hundreds of thousands of ohms or more. When you parallel those two impedances together, you get a very low value. That indicates minimal trouble with electric fields. Not zero trouble, but minimal trouble. On the other hand, the load impedance is a very large value. That indicates a lot of susceptibility to magnetic fields. This explains something that took me a while to figure out. Of course, you probably have known it a long time ago. But the biggest trouble of our four that we've been talking about, the biggest trouble is conductively coupled noise. But why is magnetic field coupling in a close second place? Why is it generally more trouble than, say, electric fields? Well, we mostly have voltage-driven circuits. We have circuits that have a very low source impedance frequently. That makes them somewhat immune to electric fields. But they have a very high load impedance. That makes them very susceptible to magnetic fields. So because we build 90% of the time voltage-driven circuits, those circuits are susceptible to magnetic fields, not much to electric fields. That's why magnetic coupling is such a significant problem for us. What if we had a current-driven circuit, like a 4 to 20 milliamp current loop? Well, in this case, we're dealing not with voltage now, we're dealing with current. The signal level is in the form of a current. We have to keep that in mind. The source impedance in this case has a high impedance, ideally infinite or very high, and the load is just a current to voltage converter, which if in the case of an op-amp could be a very low resistance. So the impedances we're dealing with now are just the opposite of what we had in the previous example. But now we're measuring current. And this is a little more complicated. We don't have the time to go through it in detail, but I would suggest if you're thinking about using a current-driven circuit, you investigate that further. They have some natural immunity to noise that's better than for a voltage-driven circuit. Look at this loop right here. Supposing there was a magnetically induced voltage in that loop. Would that induced voltage cause the loop current to change? See, we're not concerned about how much voltage is induced. We're only concerned about the change in the loop current because the signal is in the form of current. But the magnetically induced voltage does not cause much change in current because we've got a current source. We've got a very high impedance current source. It does have some effect. Current loops are slightly susceptible to magnetic fields, and they're somewhat susceptible to electric fields. But both of those factors taken together, I would say that current loops have less noise susceptibility than voltage-driven loops. Voltage-driven loops are very susceptible to magnetic fields and cause a lot of trouble, so that makes them the worst of the two, generally speaking. Let's look at another one of our equivalent circuits. I'll actually build up to that. We want to now talk a moment or two about electromagnetic waves. How do they happen? What kind of a circuit does it take to cause these problems? A little review of some antenna theory here. Let's say we have an RF generator on the end of an antenna, a wire. No connection off on the other side here. In another case, we have the RF generator, the high-frequency source, between two elements of wiring. Which of these circuits will radiate the most? Well, no question. This one radiates by far the largest amount. Theoretically, the top one has no radiation. Theoretically. In practice, you see what's going to happen. There really will be some material over here, and there'll be some capacitive coupling to that material, that metal that we forgot about. And so this circuit, if we tried to build it, probably would radiate, but it would be because there was something over here that we ignored. But if there is nothing connected over here, then this source, where the antenna is on the extreme end, it cannot radiate. So we'll keep that in mind. That'll help us in deciding how to build some circuits later on. What does it take to have electromagnetic radiation problem? You need an RF generator, high-frequency generator, and you need an antenna. And you actually also need some way to couple between the two. In the situation that I show here, a digital circuit board inside a metal enclosure with an external cable coming out. What would be, well, the RF generator would be the digital circuits. They're the high-frequency source. What could the possible antennas be? Well, looking at this circuit from the outside world, looking at it from the outside, you see this metal in the cable, and you see this metal in the chassis wall. These two pieces of metal could form a dipole antenna and be the radiating or transmitting antenna. You say, but there's also metal on the circuit board. There's metal on the circuit board, but that's inside. Viewing it from the outside, we don't see that metal. It's the metal you can see from the outside, and maybe it's not metal that you can literally see. It's metal that's exposed electrically. If it's got a dielectric coating over it, it's still exposed to the outside world. So when you look back at the circuit and you're trying to identify what are the possible RF transmitting antennas, that what metal surfaces are exposed, electrically exposed. Those become the possible elements that could make up a dipole antenna. So now kind of reviewing here, what does it take to have an electromagnetic wave emissions problem? We need an RF generator. Digital circuits would be a good example. You need to have that RF energy coupled somehow to an antenna. Now the antenna is going to be any external metal objects, like cables and metal chassis and so forth. But here's another big part of the problem, the coupling mechanism. How does that happen? Well, assuming it's occurring over a short distance, electrically short distance, it can be anything but electromagnetic wave, which means it could be a conductive problem, it could be a magnetic coupling problem, or an electric field coupling problem. One good way to reduce electromagnetic emissions is to get rid of the coupling path, or to reduce the coupling path. Sometimes it's not easy to find the antenna. In fact, sometimes when you find the antenna, you realize that it's a necessary part of the circuit. And usually when you find the source of the high frequency, you realize that's a necessary part of the circuit also. Now maybe a little filtering can be done to reduce some of the high frequencies, but the surest way to fix an RF coupling problem is to get rid of the coupling mechanism itself. That is usually not required. So here's kind of a quick summary of what we could do to control electromagnetic emissions problem. Identify the source and reduce the high frequency content by filtering. Identify the coupling mechanism. Sometimes we've got circuits that produce too much stray magnetic field or too much stray electric field. Maybe we can use self-shielding, which we'll talk about in a later session. We use self-shielding to better contain the stray field so we don't couple to the antenna so readily. Or we can try to reduce the effectiveness of the antenna. If you've got something that's acting like a dipole antenna, why don't we just short the two elements of the dipole together? Then it's not such a good antenna. Probably sounds a little too easy, right? Well, here's a general rule. To reduce electromagnetic emission or susceptibility, if we can keep all metal surfaces, all metal structures that you can view from the outside, keep all those structures at the same RF voltage, either by a metallic connection or by a capacitive connection, one or the other, that can reduce the antenna action. That can reduce the high frequency emissions. So a conclusion would be something like this. We would either want to directly bond or capacitively shunt filter or shield all the wiring that comes out of a metal housing. If there are high frequencies inside that could possibly come out on any or all of these wires, then by these three methods we can control the emission of the RF. And we can also control the reception coming back the other way. All input-output wires either directly bonded or filtered or shielded. With one of those three techniques we can control that kind of problem. We have time for maybe one or two other examples. Let's say we have AC power coming into a switching device, a load on the AC line that generates considerable amount of noise, and another load on the same AC source that is susceptible. Well, one good possibility is that this switching action puts transient noise currents back up onto the power bus and they propagate over to the other circuit. If we can prove that that is the problem, then that's a conductively coupled problem. And we're going to see that the way we fix that is with some kind of filter. Now we have an entire session devoted to filtering later. There are frequency selective filters, surge suppressing filters, and so on. We'll have to do a little discussion about what kind of filter to put on there. But if we know it's a conduction problem, we know to use a filter. In this situation here, I have a microprocessor, digital circuit with a heat sink. And let's say there's electromagnetic radiation coming off this circuit. How could this be happening? Well, one possibility is the microprocessor is developing a voltage on the heat sink relative to the plane of the board. The heat sink is a capacitor relative to this cable. So capacitive coupling from the heat sink to the cable, we get common mode current on the cable, and that cable current then causes electromagnetic radiation. Well, this concludes session 3. We'll be back with session 4 shortly.